Okay, girls, we're looking at some harder questions to do with exponential functions, and this is on the worksheet that's loaded on Moodle. So I'm looking at exercise 13a, question 5c. So if you look at the question in blue, find the gradient of y equals be k to the x at the point a, comma be ka, and show that the gradient is k times the function is k times the height. Now the reason I picked this is because there aren't any numbers, there's just letters, so it's like a general case. So let's just make sure you understand what's happening. Okay, so this is the function and this is the point. So if I put a where the x is, okay, if I put a there, you can see that I've got now B-E-K-A. So that's what's happening. X is A, so that's why it's B-E-K-A. But the question wasn't asking to prove that. I'm just trying to help you there. So the question is, show that the gradient is K times the height. So the first thing is we need to find the gradients. Now, if Y is B-E-K-X, the derivative of Kx is K. So that means the K comes out the front and joins with the K, with the B to make a new coefficient KB. And then exponential part doesn't change, so it's just KBE KX. Now, what I've done there in this next part is you can just have a look that I've separated out the BEKX, and that value is the value of y. So I've got the derivative equals k times the function. So I've shown that the gradient is k times the height, because the height is the function. Okay, so I've answered the question. So the gradient equals k times the height of the function, because the height of the function is y. So I've answered the question. So copy that and come across when you're ready. Okay, so now looking at question 10b. So I'm picking random questions that look a little bit difficult. Okay, so again, the question starts with the word show, which means that it's going to work, and if you don't get the right answer, then you go back and find your error. But show means it's going to work. Now, the function is a little bit messy. You've got some exponentials, some normal letters, and a number. Okay, and we're trying to show that this exists. So we've got a left-hand side and we've got a right-hand side, and we have to prove that the left equals the right. So first thing you do is we've got the function y, so we can find y dash. So first of all is multiply by the derivative of minus 3x, so the minus 3 comes out the front, and then exponential stays as it is, and then x turns into 1, and then 1 just disappears, so the last part's gone. And then the second derivative is multiplied by minus 3, which turns into positive 9, and then just leave the exponential part, so that doesn't change. So now I've got y dash and I've got y double dash. So the left hand side is y double dash plus 2y single dash minus 3y, and so I just substitute in these values. So there's my y dash, y double dash, sorry, there's my y dash, and that is my y. Okay, so they're all coming from there, there, and there. And then I just multiply out. So rather than going a really long line, I'm going to line them up underneath each other so that like terms come together. So the first term is just that one, and then 2 times minus 3 is minus 6, e to the minus 6. So I'm lining up like terms in this direction. 2 times 1 is 2. Now I've just pushed it across because there's going to be an x term in the middle, because, well, I don't have to, I could have had the 2 there, but I just moved it across. And then the last thing is minus 3 e to minus 3x, so I put it there, so I've lined up so the like terms match up. And minus 3 times x is minus 3x, and minus 3 times minus 1 is plus 3. And then I'm just going to add them up vertically. So 9 minus 6 minus 3 is nothing. Okay, you got no x, got none of that. Then you got minus 3x, doesn't have any partners. 2 plus 3 is 5, and that is exactly the same as the right hand side, which is what I had to prove. So I've got QED. So there's some other ones to practice that look like that. So don't get scared, you just got to work out the left hand side and make it equal to the right hand side, and then you finish with QED, which is how you finish proofs. So copy that and come across when you're ready. Okay, so this next one looks a little bit harder. Question 18a. Find possible values of lambda. This is just a Greek letter, like X in the Greek alphabet, such that that makes y equal e lambda x a solution of this equation here. So again, we've got this second derivative, we've got the first derivative, and we've got y, and we're going to put them all together and make them equal to the 0. Okay. So, and part B of the question, so part A is that, part B is when will there be no real solutions. So this is about, you know, something that can be actually found, okay, as distinct from unreal. So the first thing you do is, if nothing else, at least find the derivative and the second derivative. So first derivative, the derivative of lambda x equals lambda, so lambda comes out the front, so I've got lambda e to the lambda x, and then the second derivative is the derivative of lambda x is lambda, so the lambda comes out the front, becomes lambda squared e to lambda x. So I find the first and the second derivative. Now the left hand side is this mess here, and we're going to make it equal to 0. Okay, so it says a lambda x, so I just stick an a outside the front of the second derivative, and then it says b, so I just stick a b in front of the first derivative, and then it says cy, so I just stick a c in front of y. Now this is interesting in that there's a common factor of e lambda x, e lambda x, e lambda x, so I take that out the front as a common factor, leaving behind a lambda squared plus b lambda plus c. Now this is equal to 0, the right hand side, which means that either this number equals 0 or all of that equals 0, because it's two numbers multiplied, either the first equals 0 or the second equals 0. And this first part never equals 0 because it's an exponential function. Okay, you know that it doesn't ever equal 0, it asymptotes, but it never equals 0. And the second part is the only part that can equal 0. And if you note, you've got a lambda squared plus b lambda plus c, so this is what we call a quadratic. Now, to solve a quadratic, we use the quadratic formula. And so the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac over 2a, and that's all you. So lambda equals negative b plus or minus the square root of b squared minus 4ac over 2a, and you can't solve it, but that's what the solution is. Okay, that's possible values of lambda. And this last part, all it is inside the square root sign, you must have a number that can square root. And so the only thing you can't square root is you can't square root negative numbers. Okay, the square root of a negative number is called unreal. And so we just don't want a negative number. So when that number is a negative, you don't have real solutions. Okay, so inside the square root sign here, you have to have a positive number or 0. If it's negative, it's not real. And so when b squared minus 4ac is less than 0, it's called unreal solutions. Okay, and that's the end of that question. Okay, so copy that and come across when you're ready. Okay, so this last one, we've got 2 more questions to go. When I saved it, it went skinny, but hopefully you can still read it. So this is exercise 13b. Okay, so the first part is, again, we've got a complicated function, but you have to show that it has an x-intercept as 1. Okay, so you're told the answer, and you just have to show that it's right. And then the second part of the question, which is more interesting, is find 2 turning points and their nature. So that just means a min TP and a max TP. So that's the last part of the question. Okay, so the x-intercept, first of all, x-intercept is when y equals 0. Now y is e minus x squared ex, and you're told the value of x equals 1. So you just put x is 1 there and x is 1 there. So 1 squared is 1, e to the 1 is 1, 1 times e is e, e minus e is 0. So y equals 0, so that means that x-intercept at 1 is a true statement. Okay, so you use the value and knowing that an x-intercept is y equals 0, and you finish the question off. The second part is turning points, and as soon as you see a turning point, you need the derivative. Now, this number here, so this function here, has 2 parts, but this e is just a number, so when you derive a number, you get 0, so the derivative is just going to come from this second part here. Now, I'm not going to worry about the minus sign, I'm just going to put the minus sign out the front, but then I'm going to use the product rule, and then u v dash plus v u dash. So I get this value with a minus sign at the front, and then what I did was factorize xex comes out the front, leaving behind x plus 2. So all I've done is I've factorized it. Okay, it's just a simple factorizing, common term. Now, at the turning point, y dash equals 0. So if that's going to equal 0, then the front number is going to be 0, or the second number is going to be 0. Now, e to the x can never equal 0 because it's exponential, which means that the first value is going to be 0, and the second number is going to come from the bracket, and the opposite of x plus 2 is minus 2. So our two turning points are going to be at x equals 0 and x equals minus 2. So I've proved that there's two turning points. It didn't ask me to find the turning points. It just said show that there's two turning points. Okay. Now, I don't need to find the y value because it doesn't ask me to, but I just found there's 2 points. But I've got to classify them into a max and a min. Now, the second derivative would be, I could take my first derivative and derive it, but it's probably easier to use the first derivative test, and a negative to a positive or a positive to a negative can tell me a lot about the things. So 0 and minus 2, 0 and minus 2 are your 0 answers, and then pick a number to the left, number to the right, number to the right again. So you can see that left and right between the numbers, and then what I did was I put those numbers minus 3, minus 1 and 1, I put them into that function there. Okay, I'm trying to find y dash, so I stuck it into the y dash formula. You can go back and look at it again, but the signs go negative, positive, negative. So this is a min TP at minus 2, and it's a max TP at 0. And then when I went on to Desmos, I sketched it, and this is what the sketch looks like. So I've got a maximum turning point at 0, and I have a minimum turning point at minus 2. So it actually made sense. Whether you have access to Desmos in the test, I don't know, but it did actually prove that there were two turning points with a min and a max. So copy that down, obviously go back and get rid of all the scribbles, but that's how that one's done. And I think we've got one more question to go. Okay, so this last one is trying to go back, again, I picked out the hard question, question 17, find the equation of the normal to y equals e to the minus x squared at x equals t and determine the x-intercept of the normal. Okay, so first thing you do is, you've got a function, and the first thing you do is find the derivative. Okay, so the derivative of minus x squared is minus 2x, so that goes out the front, and then the e just stays the same. And so at x equals t, the value given in the question, I put t where x is, and then just to make it make that more sensible, I turned it upside down. So y dash is minus 2t over e to the t squared. So this negative comes to the bottom and makes a positive. Now, that's going to be the gradient of the tangent. So the gradient of the normal is, you just flip them upside down and change the sign. So that's my gradient of the normal. Eventually we have to get y equals mx plus b. That's what we're looking for, because we're looking for a straight line. So I need the y value. So next thing I do is at x equals t, y equals e to the minus t squared. And so then I just plug it in. So I've got e to the minus y equals mx plus b. And then the t's cancel out. Okay, so that cancels out with that. So I've got e to the t squared on 2. And then to find b by itself, I just move that to the other side. And so it's going to be e to the minus t squared minus e to the t squared on 2. So it's a little bit off the side there. Okay, so the equation of the normal equals y equals mx plus, and this is all b. Okay, so mx plus b. And that's the answer to the equation of the normal. The last part is a little bit harder. Okay, there is a part C which we're not going to do because we're not doing logs, so don't worry about part C. So x-intercept. So the x-intercept of the normal is when y equals 0. So I made 0 equal all of that mess. Okay, that looks right. I'm just going to pause for a sec. Yep, I'm back again. I was just checking. Okay, so what I've done is I've left that. Okay, so this is going to be 0, and then I took those two numbers across the other side. So this plus number became a minus, and this minus number here became a plus. Then to get rid of this number at the front, I cross multiply. So the 2t comes to the top, and the e to the t squared goes to the bottom outside of that number there. And then all I did was I multiplied in. So e to the t squared times e to the t squared cancels out. 2 cancels out with 2, so I've just got t by itself. Okay, and then I've got to multiply this number by this number, and so 2t 2t stays as 2t, but I'm not got a minus sign, so it's minus 2t, and then e to the t squared. So I'm multiplying, but I've got a minus here, so that's going to be 1 over e to the t squared. So I'm multiplying e to the t squared by e to the t squared, so I've got e to the 2t squared. So just remember this one here is the same as 1 over e t squared because it's a minus, but it's a minus at the front. So 2t times minus 1 is minus 2t. E to the t squared times e to the t squared equals e to the 2t squared because we add. And then here I've just finished off by taking out the t as a common factor. So t bracket 1 minus 2 over e 2t squared. Okay, and that's the x-intercept. Okay, and that's the last one. So I'm just showing you some of the hard questions which you do need to engage in because these are the questions that I will put in at the end of the test. Okay, thanks, bye.